Next piece in line on this model is the cone pulley. This particular kit came with 2 cone pulleys, which they were so nice to supply. We have the one for the main drive, and the other one is for whatever mechanism you're going to use to drive it, and they should be opposed to change the gear ratios. There's about 40 thousandths, about 1 millimeter worth of extra material all the way around on this. And this is an interesting setup. This is part of the back gear mechanism that goes all in here. And I'll tell you, when this is put together, it's pretty cool, but I am very disappointed with the fact that this is not a functional bullpen. It will disconnect the gear from the step pulley, but it's not the kind that you can reach in there and pull out like an old South Bend. I'm sure a lot of you guys are familiar with that. I'm going to make a brass arbor for this. First thing I'm going to do is clean it up, of course, so I can do something with it as far as holding it is concerned. There will be some pressure turning, there will be some drilling, there will be some reaming. And after that, we're just going to make an arbor, screw it down, and have at it. One of the features on here that's going to be not difficult to do, and it's probably not critical, is this radius right here. A 1-inch diameter crown radius. And that just means, I mean, it's a crown radius, but you can have a 1-inch diameter on a 500 diameter, so all that means is just what it says, a crown radius. 1 inch long, 250 steps, 1/8 inch, give or take, incremental steps on the way up, and this should be relatively easy. This 312 diameter here is a press fit for this component right there, and this component slides on the spindle, and everything just articulates, free wheels. This, not so lucky. This has to press fit on here or screw down. I would rather see a press fit, but that's going to be a little tough to do. All right, let's clean these things up, cut some metal. First step is make the pressure turn arbor. This is not a big deal at all. If you're going to pressure turn anything, make sure it's not going to migrate back into the collet or chuck. That you don't want to do. 7/8 diameter brass. I'm going to turn it down to 750, then reverse it and put in a 3/4 collet, and it's not going to go anywhere no matter how much pressure you put on it. Knowing that I'm going to be holding on a larger diameter, I have a small recess in the face of this to avoid the chance of the part rocking if the tool is off center. It's the only reason I just did that. I will face it again for smaller diameters. With the part securely pressed against the brass arbor that I just made, I'm going to turn the 4 diameters that are required. I know that from contacting the tool to the face, I'll tell you what, I'll just show you. Once you have your slug turned and reversed and put in a smaller collet, it's not going to migrate into the collet with pressure. Take a dust cut on the face and zero out your digital, your dial indicators, or whatever method you use to track the carriage movement. Now with the tool zeroed to the face of the arbor, any cut that you make on here, you'll know exactly where that cut is located. Knowing that I want to remove this at a later date, I'm going to move all the way out to the end, and I'm going to face the end and turn the steps. Well, let me move my hand so you see it. I'll move the tool all the way out to the end and take a face cut as close as I can get to the driving center. And so long as the tool does not go below the required overall length of the part, I'm good. Well, that'll make a whole lot of sense here in a second. Let's stick the piece on here. And go with a very slow RPM and tap it till it runs true. That ain't it. Okay, the part is adequately running true. I know that when this piece is finished, it's 1 inch long. Knowing that the tool is zeroed on the back surface, I need to stay within that 1 inch range in order not to blow this part. I want to leave a lot of material in the back, so I'll do all my work in the front, watching my digital not to go below the 1 inch mark. As a matter of fact, I want to leave it 1 inch 30, 1 inch 25, so I can turn it around and face the ugly off the back. It's a matter of turning 4 diameters, concentric, and 4 shoulders. 1, 2, 3, 4. And then I'll flip it around, face the back off, and we'll put the through hole in before it mounts on the arbor for the radius features on these steps. The steps at this point are just going to be a visual reference for the form tool at a later op. Do it. If you are going to pressure turn something like this and there's a through hole to be placed in it at a later date, make sure whatever center is in contact with the part is a smaller diameter than the through hole. So whatever nub is left underneath that center will disappear when the hole is pushed through. Simple. All right, here's a little piece of shop trivia for you. If you're ever turning an extremely soft material, gummy, sticky material like this cast aluminum is, and the finish goes from very nice to crappy to very nice to crappy, that is because the material is cold welding to the face of the tool, and under pressure, the additional cutting forces knock the chip off of the tool, and it cuts better. That's the shiny part, and then it builds up again, and that's the torn part, and then it cuts better again. So it's a lather, rinse, and repeat scenario. When that happens, you're going to need to stone the tip of the tool. I'll show you what that is. It is easy to throw terms around when you are comfortable with the terminology, but for those of you that are not experienced enough or have ever been exposed to it, when I say stone the tool, because you have galling or cold fusion, right at the very tip of the tool where it cuts, right there, drag your fingernail across the cutting edge, and if it hangs up, you got something stuck to it. We do have a term for that, but in order to maintain the G-rated rating of this video, we're just going to not tell you what that's called, but it's fly excrement. Let's put it that way. You got some fly excrement on it. You need to get that off. Sometimes simply applying pressure to the leading edge will be sufficient to dislodge it. Sometimes. Don't apply a lot of pressure. If it's a carbide tool, you can chip the tool. If that doesn't work, take a file to it, take a stone to it. And by stoning, I'm talking about we're just going to lay a nice stone across the front ground edge, roll it back and forth. Feel it again. Still present. And let's go for the top. Be very careful when you stone the top of your tool to remove the, you can see it in the reflection, that little shiny part right there. That is not supposed to be there. Make sure that your stone is in line with the rake of the tool so you don't wipe out your cutting edge. Front as well. All right. No more protrusions. Put it back in the machine. Not all you guys that are going to type comments about why don't you just make this from a piece of bar stock, do the entire part and part it off. That would be the absolute perfect way to do this. But I'm going to go with what's in the kit, and I'm going to do it like you have to do it if you don't have bar stock. If this were a continuous aluminum bar, that would be the ideal way to do it. The piece could take the pressure from the form tool, it could take a bore and ream operation, and it could take a part off, and you'd be done. But now I got to flip it around and got to face the back off to the overall length. Then I'm going to put it back in, maybe locating on the ID under pressure and put the radius on. But right now I'm not going to put the radius on the journals here because I just don't trust it from the pressure. It's going to be a lot of surface contact and I don't want to see it jump out. Okay, let's take it out, flip it around. Each one of these is a nominal imperial size, so it's going to make it real easy to hold. Say once you know the OD is running and the face is running true, go ahead and put the mounting hole in. Can't argue with that. In order to guarantee that the reamer is going to track true through this part and not follow the drilled hole predominantly, I'm going to put a small lead on the size of the finished hole. High-speed steel straight flute chucking reamer, 6 flute, 320 RPM, WD-40 as coolant. Do not hesitate at the beginning. If it chatters, it could be a problem. Feed it right in. Alright, a shorty look at the parts. They are not complete yet. The diameters are all still straight and not domed as called out on the print. One of these belongs in the lathe and the other one is the drive mechanism from whatever outrigger I will rig up. And rest assured I will. Got to put the bullpin hole in the back and then we'll mount it back on the arbor and put the radiuses on and stick all the gears on. Stay tuned. Before I move on to the crown radius detail, I'm going to put the 3/32 feature in the end. Now, if you're building this and you have a precision issue or fear of hitting this with the mating gear, this can be a slot. It can be a small elongated feature because it's strictly a driving feature for the set screw that's in the headstock gear. I'm going to do this in a 5C collet in the mill. Setup for this operation is very straightforward. 5C collet block squared up with a 1-2-3 block indicated in true. The form tool is required to do those 1-inch domed radiuses, and this is my setup for laying out the tool. I have a 1-2-3 block in my grinding vise that I'm going to use as a backstop, a 7/8 parallel and a 1/4 inch wide tool. Now, the center of this tool is now 1 inch from this surface. So when I take a 2-inch blank and lay it on top, it registers quite nicely and puts the center of this radius right on the center of that tool. It's just a matter of bluing it up, scribing it, and grinding it. So let's do that. It is an exceptionally mild feature. Exceptionally mild. I'm going to do this on the corner of the grinding wheel and probably file it in. For what it is, I'm not going to lap it in. It's just not worth it. This is the same piece of brass that I used to pressure turn the cone pulley originally. I just put a 312 lead on it so it'll go down inside the bore on the part. Also fabricated a pusher for it. Big center drill on one side, turned it to the 500, which is the lead diameter of the pulley, and another 312. So it will be trapped effectively quite securely. Unlike some things in this shop. All right, I'll stick this right on here. And these diameters are finished size, so I will blue them up or black them up or whatever. And I will look for the radius to approach tangent. And that's when I'll call it a day. Let's do it. Now, this is an awful lot of work. It could be avoided by doing this out of 1-inch material or 7/8 material for that matter. So anybody at PM Research, if you're listening, make this about a 1/2 inch longer and give the buyer the option to do that. Certainly would make it 100 times easier. I'm going to bump the tool against each one of the steps to set my depth. There may be a crown because the side of the tool is relieved and it's about 1/1000 undersize on the width, but a chamfer will take care of that. So here we go. Right, that is a super mild feature. That's almost not even worth doing. But it does help keep the belt centered and tracking and in place. So I'm going to knock these corners off with a 45-degree tool at this moment. Shine it up. can see the mild crown on each one. That will help the belt track. This is the helper pulley. This is the one that will be outside the machine, used to control the spindle speed. Not the gear ratio, but it is a spindle speed thing. We do the exact same thing to the other one, but the other one has a dog hole in it for the back gear adjustment. Otherwise, it's exactly the same. Next step in the process is to press the headstock gear into the cone pulley. This was not videoed. It is just simply a turn diameter drilled piece of gear stock. I'm going to use the press fit arbor, or the pressure turn arbor that I just used to do the cone pulley for the installation to keep everything straight. And out of the vise. Next piece in line is the gear that goes on the back of the spindle. Relatively straightforward. A very primitive setup for the set screw operation. And just one tip here for you. I am trying to get the set screw directly in the center of this little boss down here, and to indicate that is almost impossible. This is also gear stock, so although it's round, it's going to be incredibly hard to indicate as well. In a situation like this, you can tram either side of your V-block if you know that your material nests in the center, and you can check that on a surface plate. I know mine is true, so I'm using the edge. And as far as the back of the vise is concerned, that will be my registration point. A 100,000 edge finder. When I kick out on the back jaw, I will have to move about 53 thousandths to get into the center of that hole, or the center of that boss. So I'll edge find the V-block, I'll edge find the vise jaw, and I will just trust that the planets lined up this morning and my hole is going to go in the right spot. Pretty sure it's going to work out. Let's do it. And for situations just like this, the double-ended center drill that I have relieved down to clear Setups just like that. Since a 1/8 is not going to go in there, this is subsurface. This will. There we go. A really good example of how dimensioning and tolerancing can come up and bite you in your butt is on display right here. The distance between these two gears is called out on the print as 1 inch. The length of this cone pulley is called out as 1 inch. Using the standard ±5 that they've given you, this could be 995, this could be 1 inch 005, at which time you engage the back gear and the insides of the gears will encounter the insides or the outsides of the cone pulley. This is a definite problem. Right here in the very corner, right there, if we were to move that gear out, chances are it could encounter that casting at full mesh. You can see just, yes it will. So the best option here is a thinner gear. I have two options. I can make another one of these guys, or I can chuck this up and dust clearance material off the insides of each one of these gears. And as much as that kills me, that's about the only option at this time if I don't feel like making new gears. So we're going to put this back in the machine. I'm going to chuck up on this 3/16 diameter on the end here, put a center in it, and dust 10 thousandths off of each side. And we will revisit this, and you can see the clearance that will be present at that time. All right, 10th thou cut off the inside of the larger back gear, and that's where you get to find out whether or not your press fit is any good. A razor sharp tool, I just recently sharpened this tool, is a big plus when you're going across a brass interruption like the gear presents. You don't have to spend the whole day trying to deburr it. And I completely expect the insides of these holes to be adversely affected by the pressure of this center, which I'm not very happy about, but it's going to happen. For something like this, the tailstock is unloosened at this point, and I'm just turning it to the point where the tailstock starts to move back. That's the only amount of pressure I'm putting on that piece, just so that it doesn't mushroom the hole. And 10 off of this side as well. I will make notes on the prints on this for anybody that's curious. Let's take a final look at the progress up till now. The only thing missing off of this assembly right now is the main spindle gear and the spindle itself. The piece of brass that's placed in there is just strictly for fit and function, and just check everything out, see how it's all working out. This would be back gear engaged because you can see the gears in the back are meshing, which in turn drives the smaller gear. The smaller gear will drive the larger gear will drive the spindle. So when you engage the back gear, the cone pulley and the spindle gear are floating. They're independent of each other. You can see how the gear ratio would change. Considerably slower. The eccentric collars that you make in the back, you can see how the shaft moves. Watch for this shaft here to migrate. Can you see the movement? It takes it in and out. Now when it's disengaged, the cone pulley should not turn that back gear assembly. And it does not. This is when you engage your bullpin on your headstock or your spindle gear, and it's direct drive from the pulley to the gear to the spindle. The back gear assembly doesn't even move. The camera moves, but the back gear doesn't. Let's see if we can get in there. Okay. That is all she wrote for today, guys. I don't have the time to make the spindle or the gear, but that will be the next installment. And I will put in the oil cup holes because I know somebody's going to ask, and there's a lock hole in the back here as well to keep this thing engaged or not. And that should wrap up the main drive mechanism for the headstock. So yeah, I hope you enjoyed that. I certainly did. Thanks for watching. Hope you're well. Joe Pye, Advanced Innovations in Austin, Texas. I'm out. And for anybody that's curious how I sleep at night with the crack in the original handle, well, I sleep just fine because I made another one. This is the original right here. This is the new one. The neck is a little bit thinner than this one, and I changed it to more of a elliptical than a conical. So there you go. No cracks on this piece. Worked out quite well.